Alright, welcome to the video for skill number 75. I can add, subtract, and simplify rational expressions and complex fractions. So for this skill, we're primarily going to be learning how to add and subtract fractions or rational expressions, and we're going to continue to employ our ability to simplify the expressions, which we learned in the last skill. Additionally, we're going to learn how to simplify complex fractions, which may require us to add or subtract. We'll start our notes on page 75A. So in the process of adding or subtracting rational expressions, one needs to find the least common multiple of the denominators. And I've listed here how to find the least common multiple. I'll zoom in on that. So to find the least common multiple, we need to factor both terms completely, or all of the terms if there's more than two, list the repeated factors as powers, and then list all different factors. If there's a common factor, use the highest power of each factor. So here in example 1, I've got the term x squared plus 3x plus 2 and the term x plus 1. So my first step says factor completely. So I factored the left term, and the right term didn't really need any factoring. Sometimes I put a 1 in there just to remind myself that there is a 1 there. Step 2, list repeated factors as powers. So there is no repeated factor, so we're fine here. It would pretty much be the same thing for step 2. And then list all the different factors. If there is a common factor, use the highest power of each factor. So we have a factor of x plus 2, we have a factor of x plus 1, and we have a factor of 1, which I didn't write in there, but if I wanted to, I could. And then our factor of x plus 1 is already accounted for. So this is our least common multiple of these two terms. And if I wanted to, I could distribute it out and return it back to a quadratic state. In example 2, we follow the same process. So our first term, x to the third minus 4x, we are able to factor to x times x minus 2 times x plus 2. The intermediate step, which is not shown, is we first pulled out an x and got x squared minus 4, which is a difference of squares. The next term, or the next expression that we factored, same process. First we are able to factor out an x, so we got x times x squared plus 5x plus 6, and then we are factoring the quadratic. So now in step 2, we list the repeated factors as powers. In neither of these terms, neither of these expressions do we have repeated factors, so that doesn't matter. And then in step 3, list all the different factors. If there's a common factor, use the highest power of each. So we have the factor of x. Here, I'll draw arrows. We have the factor of x. We have the factor of x minus 2. We have the factor of x plus 2. X has been used. X plus 2 has been used. And we have the factor of x plus 3. This is a rather lengthy least common multiple, but if we wanted to distribute it all out, we would get the polynomial, the quartic polynomial listed here. I'm going to show you the bottom two examples which do employ what I'm describing here in step 3. So let's scroll up here. So list factor completely. So in steps 1 and 2, we are able to change that to x plus 4 squared. This one was x plus 4 times x minus 4. So we listed the repeated factors as power. So in this one, because x plus 4 happened twice, we wrote it as a power. And then list all the different factors. If there's a common factor, use the highest power of each. So the common factor between these two was x plus 4. so we use the higher power of the two, because this is x plus 4 squared, and this is x plus 4 to the 1, so we use x plus 4 squared, and then we pull the x minus 4 down. The same process works for single term expressions, and I'll let you work through the details. So factor, grab one of each factor, the highest power, and then simplify it down here. I'm sure many students will be asking, is this simplifying step necessary? Will we need to do that? Unfortunately, yes, most of the time we'll need to do that because it plays into a later step for adding and subtracting rational expressions. So make a habit of remembering how to multiply your monomials and binomials. Alright, now we're getting to the meat of the lesson, which is adding and subtracting rational expressions. In order to do that, step one is we need to find the least common multiple of the denominators, which I will call the LCD, least common denominator. Step two, you adjust each rational expression to share the LCD by multiplying the numerator and denominator by missing factors, and I'll show that in the example below. Step 3, simplify the numerators. That would be multiplying them out. Step 4, add or subtract the numerators. And step 5, simplify the resultant expression. Oh, missed a T right there. Resultant expression. And step 6, identify domain constraints. So example 5, I'm walking us through exactly this process. So what we have here is two rational expressions, 2x squared minus 30 over x squared minus 9 minus x plus 5 over x plus 3. So step 1 asks us to find the LCD, so we need to find the least common denominator for these two expressions. So in order to do that, we need to factor each term and find the LCD. This is exactly like finding the LCM. I just call it the LCD because we're finding the denominator. Alright, for step 2 we need to adjust each rational expression to share the LCD. So we notice that in the first rational expression we already have the LCD, but in the second one we don't. What we're missing is the x minus 3 piece. So we multiply the numerator and the denominator by the missing piece, x minus 3. Step 3, we're asked to simplify the numerators. So the numerator on the left is already simplified. The numerator on the right we need to multiply out. Step 4, we add or subtract the numerators. Now that we have a fraction that has the same denominator, we can add or subtract the tops, the numerators. So in this case, our denominators are the same, so we can add the top pieces. So what we have is 2x squared minus x squared, gives us x squared, negative 2x, and minus 30 minus negative 15 would be minus 30 plus 15, which is that. Almost there. Step 4, add or subtract the numerators. We just did that and leave over the LCD, so our denominator stays the same. And for step 5, what we want to do is simplify the resultant expression. So we simplify the numerator by factoring it, and we see that a common term cancels out, and that's the reason that we need to do that step, because oftentimes after we've added them, a term will cancel out. And finally, step 6, you identify the domain constraints. It should be noted that in step 5, not every single equation will have something that cancels. In fact, it would be awfully weird or strange to have something that cancels in reality, but math textbooks will often create problems that do have something that cancels, just to test you on that aspect of simplifying the expression. On page 75C, I worked through another example, and what we have is x plus 7 over x squared plus 13x plus 42 minus 10x over x squared plus 8x plus 7. And my first step is to find the LCD, so I factored the denominator for this and got x plus 6 times x plus 7, and I factored the denominator for this and I got x plus 1 times x plus 7, giving me an LCD of x plus 6, x plus 7, and x plus 1. And then the x plus 7 is repeated, so we don't need to include it. Step 2, multiply the numerator and denominator by missing pieces of the LCD. So in our first equation, we were missing the x plus 1, so we multiplied the numerator and denominator by x plus 1. In our second expression, we were missing the x plus 6, so we multiplied the numerator and denominator by x plus 6. In step 3, you simplify your numerators, which I've done here. And step 4, you add or subtract the numerators, and we can do that now that our denominator is the same. X squared minus 10x squared is negative 9x squared. 8x minus 60x is negative 52x, and 7 minus, there's nothing, is 7. And we wind up getting this expression. And we can try to simplify it, see if the numerator factors. It does not factor, so we are at a complete state. All we need to do is identify the constraints. X cannot be negative 6, x cannot be negative 7, and x cannot be negative 1. Finally, in example 7, we are learning how to simplify complex fractions. And complex fractions are fractions that are composed of multiple fractions. So, in order to do this, we want to look at the numerator and denominator independently. And first thing we should do is simplify the numerator into a single fraction for this example. So the LCD is x times x minus 1. So the top is missing x minus 1 here, and the top is missing x here. There should be, oh boy, fix that mistake. Alright, so the denominator was missing the x. I've since put it in and everything works out fine. So the numerator was missing x, so we multiplied x top and bottom. This numerator was missing x minus 1, so we multiplied it top and bottom, and we were able to simplify the numerator to be this expression. The denominator didn't need to be treated any differently because it's just a simple fraction. So going back to multiplying and dividing rational expressions, we take the numerator and we multiply it by the reciprocal of the denominator. So we do that, and in doing so we find that x minus 1 cancels, and we find this to be the final form. If we wanted to, and we should, we would say 5x minus 2 over x to the third minus 4x. And that would be the final simplified form for the complex fraction. So this skill requires us to call upon two different things that we should be able to do. We should be able to add and subtract a rational expression. So if I gave you x plus 2 over x squared minus 4, and I added to that x minus 7 over x squared minus 4x plus 4, we should be able to find the LCD and use that to write the fractions with a common denominator and then add them together. We additionally should be able to simplify complex fractions, something like 1 over x plus 2x over x minus 8, all divided by x plus 4 over x squared minus 64, or something to that effect. This concludes the video. Thank you.